So I only copied L1 and L2. L1 were the thumb times, I believe, right? Thumb. And L2 were the finger times. And we were trying to see if there's a difference. This got bumped a little bit. We're trying to see if there is a difference between thumb and finger times. We decided it probably wasn't a good idea to average L1 and then average L2 and compare those averages. Because as Michael said, we're missing the association that way. We need this to be a matched pair because we have to compare one person's thumb to their fingers and see if there's a difference between them. Fantastic. So what did we do? What did we do to set the data up to create one data set?
With L3 and we L1 minus L2.
Exactly. So you stick your blinker up on L3, and this you have to make sure you put it on top of L3. It's a little different than Excel in this respect. You have to go up on top of the header of the list. And then just L1 minus L2. L1 minus L2, enter. There are the differences. There are the differences. Some are positive, some are negative. Some are positive, some are negative. What does that mean?
Negative means the thumb is faster.
Good! If you're negative, for example, this guy right here, negative 0.1 second, that means your thumb was faster than your finger. It's negative because it's smaller. This guy has a smaller number minus a bigger number equals a negative value. Awesome, Zoe. So that means if it's positive, that means your finger was faster than your thumb. And your finger was faster than your thumb. And if we're any zero, exactly zero? Yeah. Somewhere down here perhaps. Oh no, they're close. They're close. Okay? So then the idea was, let's test it. You now have one set of data. So the idea is we now need hypotheses to test. Can I erase this over here? Is it okay if I dump this? Yeah. Okay. So, yuck. Yeah, great. All right, now, ish.
Yeah.
It is. Thanks for asking. So, step one, hypotheses. We are testing an average. With your permission, I got in the habit of doing this about 1.5 years, 2 years ago. I put a little sub D here. What do you think the sub D stands for?
Difference?
Exactly. It means for average difference. This doesn't mean anything. It's simply a label to kind of cue into the fact that we're looking at a matched pair test versus one where you have a given value. And what's nice about that is the average difference, if there is none, is going to be 0. In other words, if these parents that were complaining about thumbs versus fingers have no leg to stand on, the average difference is going to be nothing. There won't be a difference. Does that make sense?
We may not know where to stand.
Their claim was that there was a... Paris. Taking notes over there. Paris trying Esquire. The claim was that some of their kids were getting shortchanged because some parents were using thumbs, some parents were using fingers. The implication of that, of course, is there's a difference in using your thumb or your finger. One should be faster. So if their claim is invalid, no difference should be 0. 0 difference would imply there is no difference and stop worrying and worry about something more important. Does that make sense? Fair enough. What's the opposite?
Not equal to 0.
Yeah, we're trying to see if there is a difference. And what's cool about doing it this way is we can see if there's a difference first. And if there's a difference in this data, we can then go back and look at it and see if it's directional. Which means we can maybe see if thumbs are faster than fingers or fingers are faster than thumbs, and then we can take it, like you did on your take-home. Your take-home, you tested the data one way. You look at the results and said, wait a minute, we were expecting it to be here, way the hell over here. Maybe it should have been over here in the first place. Does that make sense? Good? All right. The only difference, you're still going to have hypotheses from now until the end of the course. I know this. The only difference is what goes in steps 2 and 3, your test stat and your p-value. That's the only difference. And the p-value, honestly, I retract that statement. Sorry, YouTube. I retract that statement because the p-value means the same thing on all these tests. If it's big, believe him. If it's small, believe him. It always means that. There's never going to be a difference. That's the beauty of it. That's the beauty. I'm seeing. This is good. I'm seeing knowing nods. Like, okay, I'm starting to buy this now. Good. It's fantastic. It's fantastic. Okay. So, what test statistic is it going? Variable-wise, what test statistic is it going to be? It's going to be T. It's going to be a T test because this is just a T test. This is just a T test. So let me do one more thing up here. I'll put the conclusion. it appears or does not appear that there's a difference between thumb and finger. So we'll see which one it is. Okay, there's our data. There, Darla, please help me out.
It's not about that. It's something about what you just said.
Okay.
If it's a large B, we believe H naught.
Yes, there. If you want to say it, I love what you just said, and I encourage everybody out YouTube roll for this too. What Darla just said is the most user-friendly way of understanding. A big p-value, you believe this. A small p-value, you believe this. The traditional statistical way is, if you get a big p-value, there's no reason not to believe this, which is a double negative, which says the same thing you just said. So I like leaning towards your definition better, because it's way more intuitive. I've heard, the one thing I hear from students over and over again is the whole double negative thing just throws me for a loop. Totally get that. But that is the formal definition of what they are. You have no reason not to believe it. Please, Christian.
What's the test? What's the name of the test that you used?
Just a T. A T. It's number 2 in your. It's number 2 in your longer list.
Okay.
We'll get to it here in a second.
The old one's on prophecy.
Yes, sir. And it all depends on what you're testing. Are you testing proportions or are you testing averages?
And this is
Yes, because we're trying to see if there's an average time difference, because it was measured. These were measurements, right? We measured the number of seconds on each appendage.
I'm here.
Yeah, I know you are, brother. I know you are. Welcome to Tuesday. All right, so stat tests. I know we made a graph of this on Thursday, and there was some interesting stuff in the data, wasn't there? If I remember correctly, which is always suspect, because I drove to Montreal this weekend, and I'm a little sleep deprived. I think there's an outlier in this data that might skew the average. So I recommend maybe run the test 2 different times, with and without the outlier, huh? Ish, maybe, perhaps. Okay, good. So t-test, just like Christian said. We've got ourselves some data. I like that. We've got ourselves mu naught. What the hell's mu naught? What's that going to be? For a matched pair, it's always going to be 0. I've erased it now, right here. It's what was right here about 5 minutes ago. It's always going to be 0 for a matched pair, because the idea is there is no difference in the null. You're trying to see if we can get away from that belief. Okay, so we're going to put a 0 here. Love it. Love it. Where's your data list? L3. Very nice, friends. L3. Is that, oh, Bob, go ahead. Ask me that question.
Nope.
You're
I
good?
figured it out.
Oh, you're the man. You're the man. What's the frequency? 1. Good. I'm giving you the answer. I didn't realize that. There, 1. Good. So alpha 1. We're going to test does not equals.
Yep.
Does not equals. Boom. And let's just go for a draw, shall we? Let's just go for a draw. Gesundheit. All right, I see area. I see lots of area, and I'm going to see double that, aren't I? Because it's two-tailed. Actually, what's on your mind? Damn it. Yours says error. What does it say? Error what? Error quit. Go turn your plots off. Guaranteed it's your plot. You got some plots turned on that are trying to draw stuff that isn't there anymore. Almost guaranteed. You ready? T, 1.63. 1.63 what? 1.63, what the hell does that number even mean, 1.63?
Standard deviation.
Standard deviation, Susie, why do we care about that? Or, actually, I shouldn't pick on Susie because she had a hit. I could. Why do we care about the number of standard deviations, friends? Why do we care about standard deviations? Why do we start talking about it in 243? Why do we continue to care about it now? Say that again. Yes, we're trying to see how far we are away from average. What number is right here?
0.
Always 0, and literally 0 in this case, right? In the exam you just turned in, this was 0.25 for the seizure rates, wasn't it? And on the exams you did in class on Thursday, that was either 0.75 for the avian flu. Wasn't that cool? The avian flu vaccine. If you dilute it down, it still works. That's actually legitimate. I mean, I tracked it. I told you guys we were going to look at that. It was either 0.75 or some other percentage. But it always normalizes to 0. So that's why when you look at 1.63, you're like, oh, it's bumped out. It's close to 2 standard deviations, but it's still inside. And that reiterates the fact. You're almost at a 13% p-value. Okay? And I noticed some of you were putting p as 13 or 12.5%, and some of you were just going p's bigger than 0.05. Either one's fine. Either one's fine. Both of them mean the same thing as far as the conclusion goes, don't they? What does it mean? What does it mean? Does not appear there's any difference between a thumb and a forefinger, which means you can tell the parents, and this happens every single year I do this, You can tell the parents, it's totally cool. There is a difference. It's just not very nice, Zoe. It's just not statistically significantly. Who's faster on average? Who's faster on average? This is a little bit tricky. This is a little bit tricky.
No, the thumb.
Oh, good. We got dissension among the ranks. I love this. It's a positive t-value, right? It's a positive t-value, which means the average is positive. Now, I'm going to do one more thing if it's okay with you guys. One more thing. I'm going to go to stat tests. I'm going to run the t-test on calculate versus draw. And the only reason I'm doing this is so you can see, here's the same stuff we just got. But it also tells you the sample average is 0.126. And that's 0.126 seconds. Not standard deviations. It's coincidental that they're almost exactly equal to themselves. That's highly coincidental. Because that's a percentage and that's an actual time element. So the average difference between the thumb and the forefinger are 0.126 seconds. About an eighth of a second difference. Okay? Who's faster? Why is L1 faster?
It's a positive number.
Well, that means L1's bigger, doesn't it?
Yeah.
So that means the finger's faster,
Faster.
doesn't it?
Yeah.
If L1, you guys are correct in saying L1's bigger. L1 is bigger. Bigger minus smaller equals positive. But a bigger number means it took you longer to actually compress the button. So the finger's actually faster. Does that make sense? The finger's actually faster, which means that there's no significant difference. I mean, it's faster, but not statistically significantly, as Zoe pointed out. Is that fair? Is that cool? Should we rerun the test without the outlier to see if the outlier was affecting the data?
Yes.
We have a yes. Go ahead, Christian.
Is there any way, like through doing this, we're going to see like what is the amount of time that would grant it significant?
Yes. Hold that thought. It's a 3-page problem in your homework, but it walks you through how to address just that question. And it's a tad bit outside the scope of what. Again, I told you I'm one of 3 people in the state that teaches non-parametric stats. I'm one of 2 that teaches the idea of power of a test. And I do it because it's not technically in the curriculum. I put it in that homework question. But you'll have a nice walkthrough of how to do that.
The next homework?
The one for this stuff. Yeah, for this stuff. You'll actually, great question. Perfect question, actually. And a good one. Like, how many should I sample if I think there's a difference of, say, at least an eighth of a second? How many should I sample to make it significant? So you'll get into it, I promise. It's a great question. I used to try to do it in class. Terrible idea. Because it takes about 3.5 hours to do it in class. For some reason, it takes a fraction of that in homework, which is great. So students seem to get it better in a homework context, which is great. Fair enough?
Yeah.
So, another question. I'm going to throw a couple graphs up real quick. I'm going to turn plot 1 on and plot 2 on. Looks like these are still set up from last time. There they are. Okay, let me flip some windows here. Let's go negative 0.2 to positive 1.4 by 0.1. Okay, this is essentially what we had last time. And I was very excited about this data. What's up, Ash? Oh, just stand up then. Stand up. You're awesome. And it looks normal, and I say normal, I mean normally shaped data, as Natalie said earlier, except for this guy over here. Should we remove that guy and rerun the test? What do you think?
Yes.
Might we get different results? We sure will get different results. Might it change our conclusion?
Yes.
Good. I heard dissension among the ranks. Let's take it out. Let's take the outlier out and see what happens, okay? That outlier is the value 1.1. Let's go into L3. Let's go into L3 and remove that. There he is. He's down here in spot 15. At least on mine he is. I don't know if it's in the same place on yours.
So do we take out?
And just press delete, the DEL button, which I know you hardly ever press in the TI because usually that erases your list name, which is a bad thing. But that'll just pull him out. Fair enough? Now I'm going to go zoom stat again. There's my data now. I can futz with that some more. Negative 0.2 to 0.5 by point. Let's go by 0.5 this time. Whoa! Holy hell. Oh, 0.5 is too big. 0.05. That's what I want to do. Look at that. It's freaking gorgeous. But now, look what happened. We have a second outlier. Now, that wasn't there originally, remember? That wasn't there originally. And remember how the TI is setting up outliers. It's setting up outliers via that IQR. And because your data set's pretty small, the IQR just changed dramatically by removing the one value. I say leave him in. It's a small data set. That's okay. The other one was ridiculous. I mean, 1.1 was so far away from typical. Not that you were ridiculous, those whoever gave me the 1.1. I didn't mean that personally. You can punch me in the face later if you want to. Heard it here first. So let's rerun the test and see if our conclusion changed, shall we? Okay, stat test, t-test. Let's draw. So we had a vote earlier. The vote was, is it going to change the significance of our result? Some said no, some said yes. Let's see what comes up. The lights turned on. Here we go. Double tail test, here we go. Check it out. It didn't change it hardly at all. If anything, it got a little less significant, didn't it? It got a little less significant. And that's because, what will the outliers be doing? They're going to be pulling it away from 0 if they're doing anything. If you pull the outliers out, that means stuff's going to move more back towards 0, which should be even more evidence in support of this. Does that make sense? The reason I would have, and I like finishing this problem by doing that, because when you guys are on your own running your own statistical analyses, not in a classroom setting, because you're learning the nuts and bolts here, but if you're out in the field and you find statistical significance, which means that you think it appears something is going on, and that conclusion was based on outliers from data, you might want to pull the outliers and see if the outliers are what's causing the significance versus the typical data set itself. Does that make sense? You see what I'm getting at there? In other words, the converse of what we just saw. We didn't get statistical significance even with outliers. If you remove the outliers, you're going to get even less statistical significance. Conversely, it might go the other way. When you pull the outliers, you're going to revert more towards center, which means you're reverting more towards the null. Go ahead, Susie.
It still just doesn't seem right to just pull out data.
It does if the data was a measurement error. You're correct, Susie. And her point is a good one. It seems wrong to toss data, especially when you've worked so hard to get the data. But when you look at the fact that this was a timing issue, and that time was a 1.1 second difference between thumb and finger, there's no way the race was 20 seconds long. You can't explain a 5% time difference. Somebody made a measurement error. And that's why it's okay. Outliers are tricky. There's a reason I made you guys analyze those back in 243. Your textbook doesn't even mention them. Well, it mentions them occasionally, but not to the actual scientific measuring of them. What to do with them? Research methods. Again, that course that you either have or will take. How should you toss outliers, or are they indicative of something else? It's possible. Go ahead, Michael.
Well, the one reason to toss that outlier, if we were sitting at, let's say, 2.001.
Yes.
And we chuck that outlier out, and then all of a sudden it pulls it right back in.
And that's the point. You could get significance with an outlier that would disappear as soon as the outlier is out of the data set. So then you have to ask yourself, what's the outlier doing? Is it a mismeasurement? Possible. Is it that that person is, for some reason, in a different population than the rest of those that are in, well, I can't really see it now with this bar right here. So there's all kinds of ways to address the outliers. That one I feel pretty good about calling a measurement error, if that's fair. It's one of the few that I feel that confident about. Go ahead, Zoe, great question.
I took the outlier out, but it drew the same picture and the same number.
So that means that that second outlier we got, Zoe, wasn't influeing as much as the first one was. You mean the outlier that's right here, Zoe?
No, the very first one we took out, the
You-
0.1 or whatever. You took
Well,
out.
it looks similar, but did you get these p-values and test statistics?
I got the same ones the first time.
You sure you took it out and didn't just think you took it out?
It's not there.
1.1?
The 1.1's gone.
Yep.
Interesting. Try it again. Did you hit graph or did you run the t-test again?
I did draw.
The t-test, draw. I can't explain that. Let's take a look at break, if that's okay.
Okay.
I can't explain why it should have updated, obviously. We'll take a look. Eh? Fair enough? Cool? I want to do another matched pair analysis because I want to make sure before we move into when you actually have to have two different averages, I want to make sure that you understand the mechanics behind this. And the mechanics, friends, the mechanics are only when you have your data and you have to sausage grind it into this guy. That's the only difference. That is the only difference between the mechanics of a t-test where you've got one simple string of data and a t-test where you have two strings of data that have to be analyzed with each other. So I have a question for you. Let's actually do this.